So I'm hello everybody. I'm happy to chair the session of Yadh Hafsi. So Yadh Hafsi is now a postdoc at École Polytechnique, and he did his PhD at Paris-Sacly et Évry on optimal control problems. And today he's going to talk about optimal execution under liquidity uncertainty.
So thank you, Asma, for the introduction, and thank you to Rafiq for inviting me for the session. So today the presentation is about optimal execution under liquidity uncertainty, and this is a joint work with my former PhD supervisors, Etienne Chevalier and Batane Livat, and also another colleague at Polytechnique, Sergio Polido, who's now also at Evry. Okay, so a quick introduction about the topic. First, I will introduce the financial motivation behind the study, and then we'll describe all of the mathematical modeling behind it. So we consider the problem of an agent that wants to buy a finite number of shares within a finite time horizon. So basically, this agent can trade on the limit order book continuously, but also is allowed to have some discrete order placements that would correspond to large block trades. Okay, so also the agent observes the state of the limit order book, meaning the order flow of the buys and sells over time in a continuous manner, and several liquidity constraints are attached to this problem. So basically, when someone wants to buy or sell an asset in the financial market, they would convey some information to the rest of the agents on what their intentions are. So if you are trying to buy a certain amount of assets, basically you are going to push the price up because other people are going to see that you are trying to buy that asset, and so they would hedge themselves against the adverse selection that you would induce. So this induces several transaction costs and liquidity constraints, and we define market liquidity as the sets of these fees that we would pay whenever we will send an order to the limit order book. Okay, and so the whole optimal execution problem is about minimizing transaction costs. Okay, so as I was saying a second ago, when we send an order, we have what we call a market impact. So, for example, if you see figure 1, here we are sending a meta order, buy order. We will push the price up at the very beginning. So this is what we call the instantaneous market impact. And then once we finish placing our orders, our price impact will decay over time. Okay, part of it will decay and part of it will be permanent. Okay, so 3 main components of price impact. First, the instantaneous, then a transient price impact that decays over time, and the third component that stays within the drift of the price over time. Okay. So what we also observe in financial markets, and especially in limit order book data, is that there are several market regimes. Okay, this is a plot from a study that we conducted in another paper with my PhD supervisors again on BNP Paribas stock. And so you can see on the lower part of the plot the spread of the BNP Paribas stock on the 11th of May 2022. And what we did in this study is that we tried to categorize or in a way label regimes on an intraday basis when we trade. So one of the best proxies that we have for market liquidity is what we call the spread, which is the difference between the best buy price and the best sell price. Okay, and so we define it as a liquidity proxy because it's the cost that you would pay if you buy and sell instantaneously. And so as you can see here, at the very beginning of the day, the spread is quite large. And this means that you, as a market maker, as someone that provides liquidity, you would have higher revenue because if you place a limit order at the best buy, at the best sell, and a limit order at the best buy, then the round trip cost is higher, and then you have higher fees. And if you are on the other side of the market, means if you are an agent that's trying to consume liquidity, you would pay more basically on that part of the day. We can also see that in the middle of the day, the spread is tighter, meaning that liquidity is more abundant. And at the end of the day, here, spread is again large. And this is due to the news that are coming from the US markets, basically. So whenever the Fed has new macroeconomic news, this spikes the volatility within markets. And so spreads is larger and you would pay more in order to execute your orders. Okay. So basically, the goal of our study is to take into account all of these liquidity constraints, and they already have been considered in several aspects previously in the literature. From the price impact point of view, the seminal paper by Obizawa Wong introduced what we call the transient price impact. This paper was very novel in the sense that they introduced what we call also propagator models. And so they gave dynamics for price impacts that would decay exponentially. Then Jim Gathero and Slinko in 2010 justified this model empirically, basically, and opened the path for an abundant literature about the subject. I would mainly cite Prideaux, Jacquet, and Shreve, and also the work by Alphonse Ishii and Stinko, where they introduce general forms of market impact and of transient impact models. But so the thing with all of this work about price impact is that first, they do not consider the volumes present in the limit order book in the sense that they only observe the mid price over time. But also, in a sense, many of them don't, I mean, in order to have tractability, they would have some restraining constraints about their impact, which allows them to solve their control problem. Here we will consider a problem where we see the market impact as one induced by the volumes present in the limit order book, and I will explain later what I mean about that. Also on the stochastic liquidity part. So here in this plot, as you can see, as I showed you, there are many, the periods where liquidity shifts throughout the day is quite stochastic, okay? So we need to model these market regimes through a stochastic process. And many other papers did that also, mainly the one by Eren Bayraktar, but also Cartea Sanchez Betancourt with Alvaro, with Leandro, and also Fouquet, Jaime Saporito. And basically these papers, each of them see liquidity stochastically, but from another point of view. Some of them model it as a Markov chain, others model it throughout the delay that's induced by the order that we send to an exchange, etc. So the goal of our study is to model our optimal execution problem throughout a singular control problem where we take into account all of the liquidity constraints. So now I'm going to introduce our model setup. Asma, whenever I have only 30 minutes left, let's say, if you can notify me, and I will be faster if I need to. Okay, so when we trade in real life, what we see is what we call limit order book. And what we mean by limit order book is the several quantities available at each price limit. Here we have the quantities available at each price on the bid side, and here on the ask side, buy and sell. Okay, and so what you do is that you send an order, you check whether there is enough quantity to execute your order, whether that quantity satisfies you or not, and whether you would execute at good enough prices. Okay, and if we wanted to rigorously model this limit order book thing, so first you have to take into account the price, you also have to take into account the volume at that price, and you have to take into account several limits. So that's a highly dimensional problem. Okay, so what we do is the trick that has been introduced by Alphonse Ishii and Jacquet, where they introduce what we call the density of the limit order book. So you can see a density of a limit order book as something as the KDE of this histogram. Okay, so rather than having all quantities at each limit is modeled discretely. We just smoothen them and have the equivalent of that for all of the prices. Okay. So here we derive the impact function, the instantaneous impact function from the limit order book shape. On the x-axis are the prices, on the y-axis is the quantities that are available, and so whenever you send an order, you would displace the price. So for example, say you send an order that consumes a quantity FIX, okay? Then you would display the price. Then you would displace the price by an interval, a range, small x. Okay.
Sorry, I have a small question. FIX, it will be an increasing function or not?
Yes. Yes.
But in the figure, we have not an increasing function here. The right figure.
No. So Fi is the integral of. So Fi is the shaded area.
Okay. Okay. Sorry.
Yeah.
Sorry. I understand.
So yeah, the density in itself, we call it small f.
Yes. Okay.
Yeah.
Thank you.
And yeah, so basically the price impact function is the price deviation that you induce whenever you consume a certain quantity. Okay, which is this thing here. Great. Any other question?
It is okay for me. Thank you.
Okay, thank you. So I will move on. And so now what we do in this paper is that we introduce first liquidity regimes that I described earlier. We model them through a stable and conservative Markov chain on a finite state space. So each state of the Markov chain corresponds to a certain liquidity regime. And we also introduce what we call a volume effect. Okay. So, and this is basically our main novelty in this paper. So what happened before is that the same model has been introduced by Alphonse Schid and Prédayou, but whenever you send an order at time t plus, it would instantly replenish directly. Okay, it's as if nothing happened. So you consume this when you send an order, you consume this quantity yt, okay? But then at t plus, you would directly go back to your reference price. Here, what we do is that we introduce memory throughout the process y, which is what we call a volume effect, okay? Yt is basically the price induces the price deviation from the equilibrium price in the market, okay? And it has several components, so it always reverts to zero with a rate hy. It also has noise throughout this Brownian motion, which corresponds to the reaction of the market to our trade when we send an order to the limit order book. So whenever you send an order, there are noise traders that would live around your order, and also corresponds to block trades that happens in the market. So also when you trade, you have what we call institutional agents like, I don't know, BlackRock or whatever. Then they can send a very large order that would move the volumes in the limit order. Okay. So the price is modeled as follows. You have an equilibrium price, what we call the fundamental price, and you have a price deviation. And this price deviation is induced by our trades. Okay. What we are trying to do is to minimize this price deviation whenever we send a controlled thing. Okay, now just several technical assumptions that would serve to characterize the value function of our control problem.
Just one question, if you come back very quickly.
Yeah.
Where is the control in the YT? So I'm confused. Or it's
coming. This is
okay.
Uncontrolled. This is still uncontrolled. Give me 1 second. So I'm just going to introduce quickly these assumptions that will serve us to characterize our control problem afterwards. So first we say that the limit order book is always above a power law shape of a limit order book. This is not very restraining, but we do that just so that when you send an order with a finite quantity, you cannot have infinite prices of execution. Okay. If, for example, you say that this limit order book, if this limit order book ends here, and I want to buy more, a quantity that's higher than the volume that's available in the limit order book, then theoretically it would go to infinity if you don't bound it somehow. So that's why we introduce this condition, and the other ones are just linear increasing and Lipschitz conditions on the coefficients of our volume process. Okay, now the control problem. So what we are trying to do is, again, is minimizing execution costs. So whenever we send, we are trying to purchase a position X bar over a finite time horizon, and we are trying to minimize execution costs. So whenever we send a trade to the market, our the revenue that we have, our execution costs, from our order is decomposed as follows. You have the cost at the current price, which is price times volume, plus the impact cost that's induced by the deviation process. Okay. And so we consider a set of admissible strategies that are non-decreasing and right continuous. Okay. So we have the condition that we need to have to finish our execution by terminal time t. This is a hard condition, and yeah, we can have either continuous or discrete controls. So now these are the control dynamics. We act exactly the same as with the uncontrolled dynamics that I described earlier. We say that whenever we send an order, we displace the volume effect by dx, and then the others would react to our order. Okay. And so now I define our related value function to this control problem. These corresponds to the trading costs of the continuous part of the trading strategy, of the continuous part of the control. And this corresponds to the trading cost of the impulses of our control strategy. Okay. And so for the boundary conditions, this corresponds, this says basically that at terminal time t, we have to fully liquidate the position. And we have also the value function that has a growth at most equal to that of phi I. But this is not a condition that we impose, it's just derived from the value function directly.
Sorry, maybe. So how do you, what are the phi and psi for you? Or
phi, so let me go back quickly. Psi is the price impact, is the price deviation.
Yeah, okay. And the phi?
And the phi, I hope I wrote it somewhere, is the integral of that price impact times the volume.
Okay.
Okay. This is just standard. You go to the Alfonsi Prédieu-in-Chief, and they will give you the full description of the decomposition of the cost, basically. But so this means that this is price deviation after you send an order, okay, times the volume.
Okay, but then phi and psi need to satisfy certain conditions, right? So for your optimal control even to make sense, or not, or
yes. So the conditions that we impose are on f here only. Okay. The rest you do not need anything else. I mean, you just need that when you send a finite order, you don't have an infinite price. That's it. But again, because you have the f that's defined as the density function of this, right?
Yeah.
Yeah. Okay. Any other questions? No. Okay, I'll continue then. Okay.
And maybe I have another question, sorry.
Yeah.
And what is the I now? Because you have this IM, but you never define this IM.
Sorry. When it's earlier when I defined the Markov chain, it's I. Okay, so
the same, because now it's different one.
Yeah. So your limit order book changes. The form of the limit order book changes whenever the liquidity regime changes. Okay, so this form that you see here, if you have smaller liquidity, for example, it would have this shape. Okay, I mean you can have whatever shape you want, but I mean it just defines the form of the limit order book for several liquidity regimes.
Okay.
Okay, so now just a couple of analytical properties on the value function. First, it's finite, hooray, I would say. And so it's also decreasing, non-decreasing in time. So we are trying to minimize costs. Whenever you have a smaller interval to liquidate your position, you have less degrees of freedom, right? So if your time horizon to liquidate is smaller, then your problem of liquidation is harder and you would pay more. So the execution costs are non-decreasing in time. They're non-increasing in inventory. So the lower the inventory that you have, the lower the transaction costs you have, because you have an easier problem. You move the prices in a smaller fashion. And finally, you have a non-decreasing value function in the volume effect, in the sense that, let me go back. So if you start from here, okay, if you start closer to the fundamental price, it costs you less. But if you start trading from here, very far away from the fundamental price, it would cost you more. Okay, and so finally, we also prove that the value function is continuous on the whole domain. So the proof of continuity is, I mean, for me, it was quite nice. All of you are senior researchers. I guess this is very standard for you, but basically what we're trying to do is to construct a new path of the control process so that this new path would join the initial process Y. And so basically, once you do the construction so that you would have this equal path here, you can always have a new process Y tilde, okay? That's below the initial process. And the difference between these two volume effects, you can bound it with Lipschitz functions, which makes basically afterwards the value function also continuous uniformly, jointly continuous, sorry, within all of its variables. Okay, and so since we have almost zero chance of deriving closed form formulas for our problem, even in the linear case, linear price impact, it's not very obvious whether we have a closed form formula for these kind of problems. So we chose to characterize our problem in terms of viscosity solutions. So we define the following Hamilton-Jacobi-Bellman quasi-variational inequality, where we have the continuation part and the execution part of our HGB. So the local operator here, as you can see, also includes an integral part which is coming from the jumps of the block induced by the block trees. Okay. So first we state the dynamic programming principle on the value function, and then we define the solution of this HGB in terms of viscosity solutions, basically in terms of test functions that are bounding the value function from above and below. And we prove that this value function is a continuous viscosity solution of the HGB, and also it's the unique viscosity solution of this problem. Okay, so we have a comparison principle. The proof is quite standard. You just have basically to derive a perturbation so that you show that you have a strict super solution. And once you have that, you can afterwards conclude using standard Cauchy-Lemmas arguments. Okay, so the perturbation here comes from the condition that we imposed on the form of the limit order book, in the sense that it always on the queues has to be above power law limit order book. So This condition is not arbitrary. If we go back, if we go back here, this is the condition that I was talking about. It's related to the limit order book shape on each of the liquidity regimes, okay? And it's not restrictive. First, empirically, we know that the shape of the price impact follows a power law. So, I mean, it is within the same family of these empirically studied kernels. And second, we can have more general condition on the shape of the limit order book, also just stating that when the limit of fi tends to limit of x tends to infinity here, we have a non-zero lower bound on the limit, basically. Sorry, so let's go back to these results. So to summarize now, we have viscosity solutions and uniqueness, so continuity also. And then we also study the free boundary of the problem. So basically, why studying the free boundary is important, because afterwards in the numerical part, we will use a finite difference scheme. But so in order to know whether we are converging towards the optimal strategy or not, we need to have some analytical description of the execution region and of the continuation region, so that we know whether the free boundary makes sense or not. And here what we managed to prove is that, so first, we define the free boundary as the closure of the interior of the following set. We do so because we do not know whether the value function is differentiable or not, right? So we have to define this set almost everywhere. So we need to place ourselves basically on a Sobolev space. And then once we define this set on which the value function is almost everywhere differentiable, then we take the closure of the interior to do so. So once we define the execution region, what we show is that these execution regions are connected, okay? In the sense that if you have a point, okay? So if you have a set where you say, I have to execute here, then it's connected. And if you take 2 points where you have execution, the line between the 2 points, there must be a line between the 2 points that connects them. And this line must be included in the execution region, okay? So we show connectedness. And in order to show the connectedness of the free boundary, basically, we first assume that the problem is parabolic, okay? And that's it. I think the only assumption that we assume is that the problem is parabolic, and also that the interiors of the continuation and of the execution regions are non-empty. If they are empty, then the problem is solved, right? It's either you always execute or you just wait, okay? And in order to prove the connectedness first, we prove that if we take a point, so I have a nice graph that my supervisors back in the time always criticized, but now it turns out to be quite nice. Well, so if you take a point here, okay, you know that so suppose that this point is within the execution region, all the points below are also within the execution region. That's what we show. And we also show that the axis where we have y equals to 0 is also part of the execution region too, okay? So you take a point, all of the points below are execution. If you take a point in the execution, and if you take a point on the y equals 0 axis, it's also within the execution. This in itself bounds the geometry of our free boundary. Okay, and in order to prove the following result, we motivated ourselves by the work of Caffarelli and Alessio Figali. Basically, you have to construct a test function in a way that this test function achieves a local maximum over the value function. And once you have that, you plug it within your HGB QVI and you prove a contradiction. Okay, so I mean the proof is quite technical. I liked working on it back in the time, but the main idea again is to have if you assume by contradiction that the result doesn't hold, then you have an interval where the upper part, so you take an exercise, a point within the exercise region, and you assume that there is an interval on this line where there is a continuation region, okay? And if you assume so, then you know that the value function can be bounded by a strictly concave test function within that interval, okay? And once you have that strict concavity, then you can construct your new test function and then plug it into the HGB QVI, and you have your contradiction afterwards. Okay, so next I'm going to describe the numerical results. We assume that H, sigma, and Q are linear in all coefficients here. This is just a result to illustrate our findings of the control problem. Still, we align with the literature on market structure with respect to the distribution of volumes and on the limit order book shapes. Okay, here we assume that on each liquidity regime, we have a limit order book shape that is a power law limit order book. And we assume we take default parameter values that also corresponds to the calibration parameters that are present in the literature. Okay, so first, this is an illustration of the value function when we do a perturbation of different parameters. Okay, so if, for example, we increase the intensity of the arrivals of block trades, okay, as you can see, the cost increases because here we only consider block trades that consume liquidity. So if I go back, sorry, I always go back to the same plot. I should have put it in many places, sorry. So if there is a higher probability of block trades that would push the price from here to here, for example, okay, then your cost is higher because you would on average execute from worst positions over time. So the value function increases whenever these kind of block trades happen. The parameter C corresponds here to the speed of reversion of the volume process to zero. So you want basically that the volume process to be as close to zero as possible, because then you would be very close to the fundamental price, the equilibrium price, and you would pay less fees. Okay, so whenever the reversion of the volume effect increases, execution costs decrease. And so finally, this is the parameter over the volatility. So just to remind you, this volatility term corresponds to the activity of the noise traders around the price. So if there are more noise traders that are within the market, execution price decreases. This is also intuitively intuitively also makes sense, because whenever there are noise traders, they can push the price up or down with equal probability, right? So you have a higher chance at a given price, conditionally that you are on a certain price, you have a higher chance that your price would go to the would be closer to zero when you have the noise traders, basically. Okay, and so this is an illustration of the exercise and continuation regions. Connectedness property is satisfied as you can see. So the optimal strategy that's shown in this plot is that if you, for example, are on this point, you have to execute on the axis y equals x until you reach the free boundary, and then just trade continuously here. Maybe you would have discrete trades that would push you here or here, but your your goal is always to stay on the free boundary. So now I'm going to also show the sensitivity of the free boundary with respect to several parameters. Okay, so again, if the intensity of the arrivals of the large block trades that would push the volume effect further away from the equilibrium price increases, then the exercise region shrinks. It means that you have less incentive of executing, and so you are more conservative, and you would only execute for bad volume effects. Okay. Sorry, it doesn't shrink. It expands. Okay. So now for the reversion parameter, now it shrinks. Sorry. So when you increase the reversion parameter, then you know that you will have better execution conditions over time. So you would execute at more favorable Ys. So you can choose to execute at smaller values of Y, but it's the same also for the noise trader activity around the price. So the more the number of noise traders, the more the volatility of Y is important, the more chances you have to execute at better Ys. So the more the exercise region shrinks over time. So now I'm going to show the impact of the regime changes for the exercise region. As you remember earlier, we defined or we described the liquidity regimes throughout Markov chain. So we can characterize this Markov chain throughout its transition rate matrix. Here we basically control Q1 and Q2, which are the coefficients of the transition rate matrix. And we see what is the sensitivity of the exercise region with respect to these parameters. Okay, so if we fix Q1 and Q2 and then vary the impact parameter, okay? Sorry. So if we fix both the transition rate parameters and vary the impact, then as you can see here, the higher the impact on the regime at which you are, the higher the exercise bound is, okay, the more it expands. And this is normal. It says that if I am on a good liquidity regime, I will execute more because I know that the execution costs in the regime on which I am right now are quite low, okay? But if I am on a bad liquidity regime and I expect to go on a higher liquidity regime, then I would say no. I'll just execute only on very good Ys because I expect to go on a more liquid state in a couple of seconds or whatever. These are, so for the remaining of the plots, I have exactly the same conclusions. It's just that rather than varying the parameter of the impact of our price impact, I just fix the parameters of the price impact and vary Q this time. And again, it's the exact same conclusion. Since you expect, if you are in a bad liquidity regime and you expect to go on a better one, then you execute less and wait until you transition and vice versa. Okay, so I hope I respected the time constraint, maybe too fast. But so just to conclude this work, we considered here a stochastic control framework where we had to solve an optimal acquisition problem. We considered general forms of price impacts. So if you remember, the F, a big Fi, is just a measurable function. And also we considered different stochastic liquidity constraints, first with the volume effect and second with liquidity regimes with the Markov chain. And we modeled it using the jump diffusion model. So we also incorporated a permanent and transient impact for our model, and we allowed arbitrary and nonlinear price responses. Okay, and so finally, we also characterized the value functions in terms of viscosity solutions, and we showed that this system of AGB-QVIs has a unique solution. We also had some regularity properties over the value function, mainly the continuity, monotonicity, and the connectedness of the free boundary that's related to the problem. And so finally, we gave a numerical scheme that's derived from Kant-Volchokova, a finite difference scheme to illustrate our approach. So thank you for your attention, and if you have any questions, I'm all yours.
Okay, thank you, yeah, for the nice presentation. I guess, I don't know, let's thank the Yadh. Okay, do you have questions?
Yes, please, Asma.
Okay.
Thank you, Ayad, for this nice talk and the nice topic. I have maybe a general question. Is it possible to extend the model to a random or stopping time horizon, reflecting unpredictable market events? Use stopping time?
Yes.
Okay.
So you want the stopping time to be on the bank as a bankruptcy constraint, you mean?
For example.
Yes. We did that actually on another problem, but which was an impulse control problem, but that considered quite similar constraints. You just have to take into account several. Yeah, I mean there are some technical aspects that you have to take into account, but it's quite feasible. Yeah.
Okay. I have a second question. Do you think incorporating jump processes such as Levy or Poisson jumps would significantly alter the optimal execution strategy?
Yeah, so here what we do is that we incorporate already a Levy process. So this is a Poisson process that we considered in the dynamics of the volume effect. This is a jump process here, the marked Poisson process, and it's a finite activity. It has a constant intensity, so it's a Levy. For the sensitivities, so for the impact on the execution strategy, these correspond to block trades, right? So here on the execution costs, for example, whenever you have block trades that consume a volume effect, so that put you further from the fundamental price, then you would pay higher costs. Okay. Vice versa if you have block trades on the other side.
Okay. More general question. Could AI, artificial intelligence-based calibration techniques, be used to estimate the stochastic liquidity regimes or resilience parameters from real market data?
So I'll do some self advertising. Okay, advertisement. So I'm quite old now, so I didn't use AI, but I use. So we did this using we did regime identification. Okay, on a paper with my former PhD supervisors to identify these liquidity regimes. But so we first calibrated marked events using Hawk's processes, and then we solved a stopping problem where we tried to minimize the delay of detection of these events. Okay, so you can pose the criterion that we chose back in the time was to minimize the worst detection delay possible. This is an optimal stopping time, and it's a min-max optimal stopping time, basically, that has been considered in the work of Al-Khwarizmi before. But I mean, in this paper, we extended the results to a more general class of point processes. But yeah, I mean, if you want to use AI, then maybe you can do it on like Blanca Horvatz did by clustering the volatility matrix. But yeah, I mean, there are, I guess, imagination doesn't have any bounds. So
Okay,
you can
sure.
make new things.
Okay,
Yeah.
thank you. Thank you. Thank you, Asmi.
Yes, but more questions?
Mm.
No? Because just to coming back to what Rafiq asked, so you didn't do calibration yourself, right? You just take some parameters and you did all your numerics. And is
Yes.
there a reason why you did not do the calibration yourself?
So we did the calibration on previous work, and we took
Okay,
the parameters from a calibration on previous work. Yeah.
okay, fair enough. And because I think you explained it, but what's exactly the difference to the Alfonso papers or paper? So he didn't have the y completely, right? Do I understand?
So you had Y, but all of it wasn't dynamic. So you didn't have this term, the
Okay. So
volatility
you
and
have
jump term.
stochastic. So you had just a
Exactly.
constant, or how does it? So it has a linear
Yeah.
function for the.
So
Okay.
you have an exponential. So if I go to the control dynamics rather, okay, you discard all of these parameters. You just have
So he basically
dx.
doesn't have a stochastic problem then.
Yes, exactly. It's literally a static optimization problem.
Okay.
Yeah.
And so there is no way to have a solution to the associated PDE. That's why you went to the viscosity,
Yeah.
right?
So we discuss the case where we have linear components, linear price impact here, and you can approximately have an idea of the existence and of the exact form of the free boundary. We tried to derive the exact expression of the free boundary, but it wasn't very clear in the end. I mean, so since we have also a general form, we wanted to study a general form, so we kept it this way.
Okay, I see. So even, for instance, did you think about, for example, BSTE approach, or to have this link to the BSTE solution, or you didn't even?
Yeah, but I'm PDE school. I'm not probabilistic generally.
I see. But does the problem coming from the jumps? Do you have the same even if you don't have jumps?
Even if you don't have jumps at the same.
Okay.
The problem comes from the fact, even if you don't have anything, it's just from the fact that it's dynamic.
Okay.
Yeah.
Okay. Any other questions or remarks?
Just a last question. Have you considered modeling market resilience itself as a stochastic process driven by random shocks rather than a deterministic or regime-dependent mechanism?
I mean, you mean the Markov chain I?
Yes.
We choose here a Markov chain I because it stays tractable, right? I guess you can. If you have diffusion dynamics, then I can characterize the problem as a standard stochastic control problem here. But we tried to plug in the optimal stopping rule that we derived from the paper on regime detection before, like this paper that I was talking about. Here we have the closed form formula for the optimal stopping time to detect the regime shifts, right?
Okay.
But the dynamics was corresponding to a reflected BSDE, and it became too complicated to solve. I mean, not even tractable. So the message wasn't clear. Here, the message that we wanted was relative to the volume effects, really, so that the price impact is driven by the volumes, not the drift of the price. So yeah.
Okay. Thank you. Thank you.
Okay. I guess that's it, right?
Yes.
No more questions? Okay. Then we thank Yadh again for the very nice presentation. And yeah, I don't know.
Thank you.
Thank you.
Thank you.